what we're trying to do here is to create a better developer environment for zero knowledge, to make it more accessible, to bring all the general best practices of development. So we want developers to be able to make a small app. They make some front-end UI, they make some back-end code, they make their zero knowledge code. And then they can run everything, they can test, they can deploy, all of this. So we want to make this much easier, much cheaper to develop zero knowledge apps. So we're starting this with zkInterface. And it's about interoperability of all the different software that we are building, all the projects that we have. So what we have today, we have many front ends. What I call a front end is things that can generate a secrets and that can generate a witness, so values for these secrets. And we have lots of proving systems. And this slide is a few months old, so it's totally outdated because it moves so fast. But the situation. So what's happening today is everybody, whenever someone invents a proving system, they also sort of build in front end. It's kind of tied together, and you have to use their stack. Right? That's the case, for instance, for Bellman, for instance, which appears twice. So it's both a front end and a back end, and it works by itself. Then you have in new proving systems. They look very similar in the front end side, but they just don't compile together, just a little bit different. So we put zkInterface in the middle to decouple those things and let you choose whichever language or front end or framework you prefer for the particular type of application that you're trying to write, and choose whichever proof system works best for your use case, whether it has a trusted setup or not, what are its performance characteristics. And that should be a totally independent choice, ideally. So we just put this layer. So each front end will have an adapter, each proving system will have an adapter as well, and they have a common interface. So the basic flow, when you have a front end and a back end, you need to describe the secrets. Secret is described as constraints. And later, when the user inputs some values, the front end will calculate a full witness and pass this witness to the proving system to generate proofs. So that's those two steps that you find. Sometimes they are together, for instance, with bulletproofs or things that don't have a trusted setup. They can happen together. For pre-processing snarks, it happens, the constraints phase happens as a trusted setup phase, so during an MPC, and only later the second step will happen many times to make many proofs. And we support both flows and variants of it. It's all based on message passing because things are implemented in different languages. So we are cross-platform with this. It's only bytes. We define the memory layout. So what I just explained is compatible with the different approaches, with or without preprocessing, and with I will show several examples. We use an interface definition format, so that already exists. It's called flat buffers. It's a particular syntax. We provide the spec in this syntax on our GitHub. And that's extensible, and that's also performance. So it's really a memory layout. If you are making a very high performance, very large witnesses, you can just write in memory. You can make it very fast. And it's flexible. We support many types of deployments, even cross machines or in web, and so on. So you can check the different types of implementations also on our GitHub. And we also have, so we have this description of the bytes format, and we have a spec that explains the rationale behind it. So today I would like to focus more on the deployment strategies that are possible. So what exists? There are many generators of circuits and witnesses, so languages to express your logic. And there are many proof systems. So you pick one. Then each one has an adapter, this middle part. The adapter is zkInterface. It's pretty simple. It's a very lightweight converter into a common format. And then even more lightweight, you choose how you are going to move the bytes between this piece of software and this piece of software. So is it a single process, or is it two different processes? Is it two different machines? So you have flexibilities in choosing the transports, and I propose multiple approaches there. So if you're just doing a single process, you're doing an application on a server written in Rust or in C++, you're just going to make a function call. Function just takes a zkInterface message. That's it. That's the interface. It's just agree on the name. First parameter is the message, and that's it. It's just moving bytes. Then we have, and you can interoperate between the Rust and C, C++ by a foreign function interface, if necessary. If you are in a web context, you want everything to happen in the web browser, then you can compile your components in WebAssembly. So you make two WebAssembly modules that talk to each other through zkInterface. And then your web application just glue code that copies the byte from one to the other. So again, very simple interface. And for some other use cases, you might want to be cross-platform. So that means either it's totally different processes that run on the same server or on different servers. And I will give an example of how to use with HTTP. So again, the HTTP is very simple, just moving the bytes. So we have a demonstration for web applications. So how web application could look. And here I even go as far as calling scripts, because you can edit the script. This is a web page. Everything runs locally in the browser. You can edit the script, and that will generate the secret, the witness, and generate proofs and verify the proofs, all in the web browser. So there are two modules, as I said. One generates the witness, and one does the proving and verification. So you have independent modules, and it's plug and play. So you could replace either without, and each module doesn't know about the other. They only know about zkInterface formats. And you can try it. It works. It's live. We use the Socrates language to the left, because this is what looks the most like a scripting language. But you could really edit. You could really write your UI code, your backend code, and your Socrates code, and make it all work together like this. And as a proving system for this demonstration, we use bullet proofs because it doesn't require a trusted setup. So it shows you have a very fast loop of iteration. Just change the code there, and everything works instantly. And another use case is proof of a service or delegation. In this case, this is something we use at QEDIT, for instance. We separate the main application, which runs on the server, but it doesn't have to be a powerful server. And you have a cluster of provers that are very powerful servers, and many of them, and they can be agnostic to what you're trying to prove. They just know how to execute the cryptography. And the apps just bundle together what secrets they want, what witness they generated, send it to the prover, whichever is available. You can put load balancing, HTTP load balancing in the middle, and scale your proving cluster independently from your apps. You can also do a delegation if you have an end user device and you want proofs to be faster. So someone, either you as a commercial service or maybe a third party, will provide this proving as a service for a fee, let's say. Or yet another idea is that people can run their computer or their little box that does proving at their home and have their mobile phone delegates to the more powerful computer. If you don't want any third party, that's also possible. all of this should be easy to deploy, for instance, with Docker and so on. That's the idea. Antoine?
How do you make sure that the proof is generated on the witness that is sent?
Well, you could verify it.
Right.
Yeah, otherwise it will just not verify. So you have some flexibility here to which third party or you want to reveal your witness. Maybe it's not even, you have a party provides the app as a service, whatever the app is, and another service could provide the proving, or yourself on your own computer at home. Point is that all of this should be like plug and play. That's why I put a Docker icon. Another use case is testing and benchmarking. So whenever there is a new paper or a new implementation of a paper, and every time they make a slightly different interface, so I'm saying just always start with zkInterface adapter for your reference implementation, for your new implementation, and then we can just plug it there, compare with what's existing, just run the benchmark again, run on different circuit sizes, different circuit connectivity, different hardware, and it also works as a test to verify your implementation, so we can have a test suite and so on. So there is a prototype of this on our GitHub as well. And it uses the HTTP thing. So the benchmarker, actually, we can go back to that. The servers, they are just wrappers for the proving systems for HTTP, so they could implement this scheme already. But here I put the benchmarker. So benchmarker just runs starts a proving system and then sends over HTTP the benchmark secrets request. So it's compatible. We have the more advanced use case. So far, I've talked only about front-end talking to backends. But a front-end might want to use to reuse libraries. So that's what we want. We want a developer ecosystem where you can reuse codes for other codes that has been written, that has been tested, optimized, vetted, and so on. So you make one constraint system, one statement, and you want to reuse multiple gadgets, then compose them as one statement. So this is all in what I call a front end. So this is one front end calling other front ends as a library. And the connector here that I draw, they are actually the same interface as between a front end and a back end. It's just the same interface. You have to send, instead of sending full secret, you send a part of a secret. And instead of a full witness, just a part of a witness. And the interface is the same. So each component talks over zkInterface with the other components, which might run in a different way. It might be written in a different framework. And that's the goal, to have really an ecosystem where you can choose dependencies that you want to use and have some kind of package manager to install this library, and use the gadgets. Yes?
So what kind of overhead would you expect for using this approach relative to writing everything in a single library, being able to do cross-component optimizations and global optimizations?
Yeah, that's right. So first of all, we expect the witness generation to be not the bottleneck in the proving compared to the proving cryptographic already. So, and the interface anyway is fast. Is a binary format which is fast. But you're probably talking about optimizing the secrets. So you have to make a compromise at some point. If you want to save developer time to be easier, when we reuse libraries, generally there is an interface. So people who designed it made their best guess as to where the interface of their gadgets or their library is going to be, and probably it's going to work for most people. And it's then people can decide if it's worth going and redoing it because they see an optimization in the by doing it monolithically, but that's going to be a lot of effort. Or do you want to save your time and just reuse the work for others at some performance cost, maybe, if there is such. Which we do today. We don't use the absolute fastest software that runs the fewest instruction on CPU right now, right? We do JavaScript and things like this and Python. That's the same idea. I don't expect the overhead to be very, very large in this.
I guess it depends how big the gadgets are that you
Yeah, you have to design. I don't prescribe how granular that should be. Probably it's everybody who designs their gadget have to think what granularity makes sense to not have a large overhead in this decomposition. So what we have a Bellman Graph 16 prover. We have Dalek bullet proofs prover. As front ends, we have Socrates, Lipsnark, and Mir. So thanks to Daniel Lubarov, who made the Mir. So Mir is so it's the Mir protocol, and they have a gadget library of gadgets, and they made the zkInterface adapter for it. So from spec. So that's good. From spec and examples. So this is encouraging. That's possible to just read the GitHub and make your own adapter. It's possible. We have in progress Circom and WebSnark in JavaScript. Zaxi and Marlin, which are similar to Bellman in IDs, in Rust. And we would like also to have a setup MPC, because some people are making MPC now and they have to re-implement it. Either make a variant of the Zcash MPC or re-implement it in C++. We would like to have a generic setup for Graph 16 probably that does the MPC. You just provide it a new secret as a zkInterface file, and everybody will be able to run very easily the MPC. And then once you have this, it's also more valuable to improve, even to automate more the MPC, because you know that many applications will be able to use this tool and not just one. So for us, status, so our GitHub always has the latest status. You can discuss and propose things on the ZKProof forum, community.zkproof.org, and for casual chat, we have a Telegram as well. So thanks to everybody who contributed, who reviewed. Yeah, Tom?
Just one question. I guess this is a natural next step, but are you guys interested in DSEC? Like to basically support massive circuits and so on and distribute through your cluster?
So you could do it already. zkInterface, you can split it. You have if your secret is a long list of constraints, you can split it in multiple messages. You can do that, and then concatenate them. Actually, it's supported by the Rust library already. You can. It's the same. The Rust library takes a list of buffers and just iterates over all of them to give a single view. So you can mix and match. You can do it. There's no Java implementation, but you can generate the Java code from the interface definition and try to do this.
Thank you, speaker.
Thank you.
Are there any more questions?
Yes?
Oh, wait.
I'd like to have a gadget library as well.
What was the question? Can you repeat the question?
So are we planning to offer one gadget library? So we want multiple projects. We want multiple companies to offer their gadgets as a library. So there is probably the biggest one should be Lipsnark today. So Lipsnark has a large library of gadgets. So that goes all the way to tiny RAM that you can make an entire CPU from those gadgets from Lipsnark. I mean CPU prover. Yes?
How specific? Thank you. How specific is it to R1CS? I mean, do you support things like the Sonic or Marlin or Punk style of constraint systems where So you can't do additions for free in each constraint.
Yes. So we do the bulletproof implementation, for instance, does that. So it's a conversion. So the zkInterface format is R1CS. So it's a list of multiplication, and each term is an addition of all variables. It doesn't necessarily mean that the additions are free. So for instance, in the bulletproof implementation, it looks at each term and it adds linear constraints to match them. And in graph 16, it just does the free addition.
Yeah, there are various ways of doing that, with some that impose more overhead than...
That's right. So it's also possible that some secret is optimized assuming free additions, and then there could be another optimization for non-free additions. But you could still express it as R1CS even.
I guess I will just add that it is interesting to see how, for example, the custom gates in Plunk could play a role here, or to not lose the kind of efficiency that it would gain from those. And there is definitely more work to be done to have interfaces to like Stark, air constraint systems, and so on, which is definitely interesting. Yeah.
So if those things, so when it's a proving system that is just by itself, like Stark and air is a little bit by itself, then there is no point in trying to standardize because it just doesn't work the same. Stark could ingest, they could prove zkInterface secrets. We could make an adapter for it. If we find that a new common pattern, so currently we observe that every application is R1CS or arithmetic secrets. If we find something that they are uniform secrets, like in Starks, where you have repeated computation, we could also standardize it. We could extend it. The format is extensible by design.
So the other thing that is not just R1CS would be bulletproof support for so generating challenges and operating on committed secrets. So do you support anything like that?
No.
Okay.
But you would use for each step. If you want to make multiple secrets and then some other range proof or something and some multiple secrets in a single transcript, you could still use them have other frameworks generate the secrets for this.
Okay, thank you.
Any more questions? Okay, let's thank Aurelien once more.
Thank you.